Now we're going to work an example for an undamped free vibration system. Here's the objective. Given an undamped free vibration system and its initial condition, determine the equation of motion of the mass along with its amplitude, period, and natural frequency. So here's our example. We have a mass of 1 kilogram, and we can find the spring constant because when we attach the weight to the spring, it comes down at rest 0.2 of a meter. So we multiply the mass, which is 1 kilogram, times the acceleration due to gravity in the SI system, 9.8 meters per second, and divide by 0.2 meters. And what we get out of here is 49 newtons per meter. Then it says the mass, there's the distance it stretched, 0.2 meters. The mass is then pulled down 0.3 meters below. So y at 0, remember down is positive, so we will have 0.3 meters for y sub 0, and it's given an upward velocity of 2.8 meters per second. Remember, upward is negative, so this is minus 2.8 meters per second. So here's our equation, a differential equation that models the motion. We don't have any damping, so we're going to substitute for the mass 1, and for K we're going to substitute 49, and that's equal to 0.
We'll solve this by starting with the auxiliary equation, whose roots are 0 plus or minus 7i. So that gives us y of t is c1 cosine 7t plus c2 sine 7t, and the first derivative shown here. Now we can find c1 and c2 by utilizing the fact that y at 0 is equal to 0.3, and when we plug in t equal to 0, we find that c1 is 0.3. Y prime at 0 is minus 2.8. When we plug in t equal to 0, we find that c2 is minus 0.4. So we can write y of t in this form, but a more desirable form is this one. We want to write it as a sine of, in our case, 7t plus a phase shift. So if I use my trig identity for sine of a plus b, I can write a sine omega t plus phi as a sine phi cosine omega t plus a cosine phi sine omega t. Well, if we match those up, then that means cosine omega t is cosine 7t, sine omega t is sine 7t. So a sine phi is 0.3 and a cosine phi is minus 0.4. We know if I square those terms, a squared sine squared phi plus a squared cosine squared phi is 0.3 squared plus a minus 0.4 squared. That's 0.25, but sine squared plus cosine squared is 1, so a is 0.5 meters in this problem. Now, a sine phi is 0.3, a cosine phi is minus 0.4, so sine phi is 0.3 over a, or 0.3 over 0.5, 3 over 5. Cosine phi is minus 0.4 over a, which gives us minus 4 over 5. So sine is positive, cosine is negative. We're in the second quadrant for phi. So tangent of phi is minus 3 over 4. If you want to write that, probably the easiest way to think about that in working with your calculator is to write phi as pi minus the inverse tangent of the first quadrant angle, inverse tangent of 3 over 4. That's about 2.5 radians. So a preferred form for this would be that y of t is 0.5 sine 7t plus 2.5. So the amplitude is the magnitude of this multiplier, in this case 0.5 meters. The angular frequency is 7 radians per second. The natural frequency is the angular frequency divided by 2 pi to give us 7 over 2 pi cycles per second. And the period is the reciprocal of the natural frequency. It's 2 pi over 7 seconds per cycle. We could do the problem with Laplace transforms utilizing our initial condition information all in the, as we solve the problem. Take the Laplace transform of both sides using the initial condition information, and notice we have s squared plus 49 times capital Y of s is equal to 0.3s minus 2.8. Divide both sides by s squared plus 49. Notice that 2.8 is 0.4 times 0.7. There's our minus sign, and we can invert that, and we have the form, the first form that I obtained, 0.3 cosine 7t minus 0.4 sine of 7t.
In example 2, we have a mass of 100 kilograms this time rather than just 1 kilogram, and it's attached to a spring, and it causes the spring to stretch 0.2 meters. So we can get the spring constant by multiplying the mass, 100 kilograms, times the acceleration due to gravity, 9.8 meters per second, and we're going to divide that by the distance it's stretched, 0.20 meters. And so what we get here is 4,900 newtons per meter. Now the mass is pulled down 5 centimeters or 0.05 meters, so y at 0 is 0.05 meters, and it's pulled down and it's just released. So our initial velocity is 0 meters per second. So here's our differential equation that models this. With it's free, no damping. So we have 0 for the damping factor and 0 for the forcing function there. And we substitute into here, and we get y double prime plus 4,900 over 100 times y is equal to 0. Now y double prime plus 49y equal to 0 is the same differential equation that we had in example 1, but this time we have a larger mass and our initial conditions are different.
We're going to solve this using Laplace transforms. So we will take the Laplace transform of the entire differential equation and use the initial condition information. So we have s squared, capital Y at s, minus s times 0.05 minus 0 plus 49y at s is equal to the Laplace transform of 0, which is 0. Solving for capital Y at s, we end up with 0.05s over s squared plus 49. When we take the inverse transform to find y of t, we get 0.05 cosine 7t, but we want to use a trig identity to write that as sine, the cosine 7t, as sine of 7t plus pi over 2.